Hello and welcome back to Data Science CastNet, a shorter video today partly to look at this paper, Diffusion Beats Autoregressive in Data Constrained Settings, but also just to talk about a bit of a win for open science peer review discussion on X, formerly known as Twitter. And so this paper is looking at this idea of data constrained, i.e. what do we do when we don't have that many tokens to train on? And it harks back to an earlier paper, Scaling Data Constrained Language Models from some good folks over at Hugging Face, now elsewhere. And they were talking about, this is in the original paper in 2023, talking about this like looming data wall, right? What happens when you run out of training data for large language models? And so they found that repeating the data multiple times, in other words, multiple epochs over your training data, gets you improvements, almost the same as if you're training on fresh data, right? If you're training on 200 billion tokens of text for 4 epochs versus 800 billion tokens of fresh text, you're not going to see too much of a difference. But beyond that, you start to see like diminishing returns of repeating your data. And so this new paper is going to approach that same problem, but investigate specifically, are diffusion models any different? Can they make better use of this repeated data? And they find that they do. They have this critical compute point whereby as we add more and more compute for a given amount of data, we eventually reach this point where the diffusion models, the masked diffusion models like we've looked at in a few previous videos, they start to outperform the autoregressive models. And so given like some constraints around how much data you have versus how much compute you have, it might be more valuable to squeeze more bang for your buck in terms of data points to switch to diffusion models. So that's the key takeaway of this paper. We'll look through a few points worth noting, but then I want to talk about some follow-up discussion that's, in my view, almost as or even more interesting than the paper itself. Okay, so their key findings: diffusion models overtake autoregressive models given sufficient compute. They benefit from far more from repeated data. They have a much higher effective epoch count. Effective epoch, this munning off et al. Is the scaling data constrained models, finding that for autoregressive models, at some point you're just not getting any more value from repeating your data, but for diffusion models, hundreds of epochs of repetition is still fine. And so then finally they investigate like where does this critical compute point lie for a given data set size. What's the amount where you'd cross over from autoregressive models being better to diffusion models being better? Okay, and then if you've got enough compute to just keep pushing past that point, diffusion models end up at a better point. Cool. Okay, so they're training autoregressive models, i.e. predicting the next token. Diffusion models, like we've looked at previously, some masking ratio between 0 and 1, and then replacing the tokens with a mask and trying to predict the original token. And so remember the takeaway from some of our previous videos was that the autoregressive training is very efficient, right? For a given set of input tokens, for each one I'm predicting the next token in the sequence, I'm getting a very rich training signal, but I only have one version of this sample presented to me, and if I'm repeating this again and again, it's the exact same. Whereas masked diffusion, because we're doing a random amount of masking and a random masking positions, I might see multiple different variants of the input, but because only a subset is going to be masked, it's not as dense of a learning signal, and so maybe it takes a little bit longer to be useful. Okay, so they explore this. They set up a subset of C4. They're training on 20 or 50 or 100 million tokens, training up to 800 epochs, so many, many repetitions of those tokens. Models are quite small, from 7 million parameters all the way up to 2.5 billion parameters. And they're going to use chinchilla scaling. In other words, like for a given set of compute and data and so on, we're going to use the chinchilla suggested like width versus depth of the model and try and just eliminate as many other variables as possible. Okay, and they find that this is like another way of viewing the same result. If we have more and more epochs, our loss goes down, right? So like getting the darker colors in both of these plots. But for autoregressive models, at some point the loss actually starts going up again, right? Like at some point you start like overfitting to the data or just really like losing performance with those repetitions. But for diffusion models, you can keep adding more repetitions for a lot longer, and you still continue to see a further and further downward trend, and the absolute best point in these plots is lower in absolute terms for the diffusion model. So that's their output. Okay, so that's a really cool paper, I think a really interesting result. and I want to talk about the discussion around this paper and some of the points that it brought up that are, as interesting as the original finding, maybe even more so, and also just highlight the benefits of this like open sharing and discussion. Okay, so clone of Simo kicked off the discussion. Everyone take your top 1% quality dataset and train 100 epochs right now. Basically like flagging the headline thing of this paper. Diffusion models can repeat data multiple times and still get a lot of juice from it. Isn't that cool? And then Lucas came with a take, hey, this is aka data augmentation, right? For those of us who've been in the machine learning and computer vision space for a lot longer than LLMs have been a thing, this was always the case, right? Running many, many, many epochs, tens, hundreds of epochs over your data was a thing that you could do to eke out more performance when you didn't have much data, especially for fine-tuning, as long as you did augmentation. So with images that often involve different random crops and flips and changing the brightness and so on, and using things like dropout. So he flags that one way of thinking about this diffusion objective with the masking is that it's data augmentation. You get two different versions of your training data, so it's not seeing the exact same thing in two repeated epochs. And so he says, look, I wish they'd thought of running some kind of augmentation or dropout. And that original tweet already sparked a lot of interesting discussion about what is augmentation for text, right? Rephrasing, back translation, are you randomly dropping words, dictionary dropouts, etc. There's been some past work on this that I think is really interesting, especially for specifically like fine tuning. If you've got some small subset of really important tokens that you want, rephrasing them and paraphrasing them and back translating them and so on is pretty useful. Anyway, so that was like an initial point. Like, hey, this is just augmentation. I wish they'd done some ablations. And so then, let's see, I think here, no, let's go back one. Yeah, so then one of the authors of the paper said, oh, we ran more experiments with random token masking and attention dropout. In other words, some of the potential suggestions for quote-unquote augmentation or regularization in the autoregressive training, and they still overfit quite quickly. They're still behind diffusion models trained for 500 epochs, and then offered like a sort of an additional thing that's building on, it's not exactly just augmentation. Like diffusion models are, they're not just always predicting the next token, they're having to predict the unmasking objective, for all different sets of masks and in different orders of unmasking. And so, like, hey, this is like this theory that the different variants or the things that the diffusion model has to predict is much richer as a learning signal than autoregression, even with things like dropout. So, okay, cool, that's an interesting hypothesis. And then Lucas had another great suggestion, and I think some other people chimed in with variants as well, of like, okay, well, what if we did autoregressive training on different permutations, right? So you could imagine like training on the sequence front to back, and then back to front, and then some other like possibly random shuffle or some different pattern. And as we add those like different random permutations, it'd be cool to see a plot of like, can we increase the n and see the performance, right? So that's like, okay, cool, very interesting idea. And a lot of times this is where it would die, but I really like props to the authors for diving in and saying, okay, like let's understand why diffusion models do better. And we have this, hypothesis that diffusion models learn from these different multiple token orderings and so on. Let's test this on autoregressive models by varying the number of token orderings, right? Standard left to right plus k minus 1 additional random permutations, exactly what Lucas had suggested. And as you increase this n, sure enough, like here in the blue is the standard autoregression. The best it ever gets to is right over here, like 3.8 validation loss. And it gets worse and worse and worse as you keep repeating more and more tokens, right? If you add a second random ordering that has to learn, it already does better. And by the time you've added 4 or 16, the top loss that it's reaching is kind of matching the best loss that the diffusion models achieved. Right, so this is a huge new result. They've updated the submission. I don't think it's live yet. It's definitely not in the PDF that I have, but should go in the next day or two during the archive cycle. Yeah, so it's really cool to see people suggesting experiments and then running them, and the paper improving in real time, just testing that, like, an interesting hypothesis that's a result of the original work, pushing it even further. Yeah, so I just want to say, like, props to everyone involved. Like, yeah, this Lucas calls out, this is open review, right? This is not, submitted to some conference and many months later, someone suggests a few things before they get accepted and we do it grumbling, I guess I should do that ablation just so that the reviewer will get off my back. This is like people doing science in the open, and all of us learning as a result. So yeah, I thought it was a really interesting general discussion. I think it's a very worthwhile point of view that diffusion is a different objective. It's maybe trickier and maybe harder to learn from initially, but it does allow you to repeat your data and to keep pulling more signal from it. I'm sure we'll get better and better at diffusion training, right? This current setup of it taking so long to even match the autoregressive case, I suspect as we get better at diffusion language models, maybe that'll shift to the left slightly. But even so, as it currently stands, there's this point where if you only have a very little data, and I'm imagining this probably holds to some lesser extent for fine-tuning as well, you've only got so many tokens to train on, then choosing an objective like diffusion, once you have enough compute to make it worthwhile, becomes a way to get a little bit of extra performance out. And critically now from this additional experiments, a lens that we can view this from is diffusion, mask prediction as augmentation, and maybe there's other innovative new augmentations that aren't the full like moving away from autoregressive, but instead doing things like trying some different orderings, rewriting the data somehow using an existing model if that's possible. Any other tricks that we can find for allowing us to do multiple repetitions of training without necessarily losing the benefit from that. So anyway, great paper, great work on all involved, suggesting experiments and testing them out and finding those interesting results. I hope you enjoyed this mini dive, and we'll see you in the next video. Thanks for watching.